So I want to talk about position, velocity, and acceleration for a special case of a moving object, which is when there's a constant net force on that object. And what we'll eventually get to is we'll get to these kinematic equations, which are sort of the classic equations when you hear somebody working on problems in a physics class, some ball flying through the air, something like that. We're using equations like this. So we're finally to these classic equations. Okay, so if the net force is constant and the mass of an object is constant, what must be true about its acceleration? Well, we know that F equals ma. This is Newton's second law, and it's in the pre-reading. So what we can do is we can write this as A is equal to F over m, and we know that both of these things are constant. So what that means is that A is constant too. So we have a constant acceleration. And so when we have constant acceleration, we can write these kinematic equations which link up the position, the velocity, the acceleration for any time. So to do that, we first have to put in a few assumptions. One thing that we'll assume, so we don't have to keep writing delta t, is we'll assume that we have some time that's called t equals 0, and at that t equals 0, we'll call the position of the object wherever it is at that time. We'll call that y underscore or y subscript 0, and we'll call, and here we're just working in one dimension. We're only going to work in the y direction. Just for this part. We'll get to 2 dimensions later, but right now we'll just work in y. So that's why I said y 0, and then the y velocity at t equals 0 is going to be called v0y. So here the y component of the acceleration, ay, is constant. So that's the important assumption for this special case. And so if you have all these assumptions, then at any later time, you can find the velocity of the object. Let's say it's a ball. The velocity of the ball is a function of time. You can find the average velocity over some period of time, say from 0 to t. You can find the position versus time, or you can find the velocity versus position. And so these are a bunch of equations, and you might wonder, where do these equations come from? Did they just come from the sky and they were given to us on tablets? Well, they actually come from definitions. So the definition of acceleration, which you may have read, I hope you have, is this. So that's just the definition. This is what acceleration is. The average acceleration is the change in the velocity over the change in time. So what we can do, just to get a sense of where one of these equations comes from, is that we can rewrite this equation here by separating out ay and writing vy minus v naught y over t. Now, remember that we have t final here is like t, and we also had an initial time, so our initial time is essentially where t equals 0. So we can actually rewrite the bottom. So let me rewrite the top here. Rewrite the bottom as t, which is t final, minus 0, which is t initial. And then on the top here, this vy that's at time t. The velocity of y here is at time t. So this is sort of like the final velocity, and the 0 down here means that's the initial velocity at t sub I, or t equals 0. So what that means is that we can write both of this one also as v final minus v initial, and this as t final minus t initial, or delta v y over delta t. So it turns out that this equation just comes from the definition of acceleration, and you can also derive the rest of these. You don't have to, but you're able to derive them from other definitions and concepts we know. So they don't just come to you from the sky. Instead, they're derived, but don't worry, you don't have to do it. I hope that helps.